Okay, so slope has to do with the first derivative, and concavity has to do with the second derivative. All right, so to find the first derivative, I need to do dy dt. How about we rewrite y as 1/4 t squared minus 1? Okay, so dy dt is 1/2 t. And don't be smart with me saying, you're the teacher. Just kidding. And then dx dt would be 1/2 t to the negative 1/2. All right, so dy dx is dy dt over dx dt. Which looks nasty, but the 1/2s will cancel. And then I could bring the t to the 1/2 up to the top. It would be t to the 3/2. Perfect. All right, so I'm looking for, so this is a general formula for the slope anywhere along the curve that's represented by those parametric equations. But I want the slope at the point 2, 3. Now, normally, we're used to just plugging in a 2 and a 3 for x and for y. But my slope doesn't have any x's or y's in it. Good. I could plug in 2 for x and or 3 for y, and then solve for t. But it should be the exact same thing. Good. If I plug in a 2 for x and solve for t, and if I plug in a 3 for y and solve for t, it should be the same thing. So what's the easier equation to use? X. Right. So 2 equals the square root of t, so therefore t equals 4. So the slope at t equal 4 will be 4 to the 3/2 power, which does actually simplify nicely into 8. Very nice. Okay, so not that bad. All right, concavity has to do with the second derivative. So my second derivative will be the derivative of the first derivative, which is 3/2 t to the 1/2 divided by the original dx dt. All right, first off, 3/2 divided by 1/2. 3, and t to the 1/2 divided by t to the negative 1/2 is just t. And we're interested in the same point, so t is 4 at that point. So when t equals 4, the second derivative will equal 12, meaning the curve is concave up. Do not say meaning it is concave up. If you're talking about it, I don't know if you're talking about the point 2, 3, dy dt, my dog, or the original graph, or my foot, or the elephant that's could be sitting in the room. Okay, find an equation with a tangent line to the curve at the specific value of the parameter. Okay, so equation of a tangent line is, what do I need? I need a derivative or a point, or a slope, and I also need a point. Good. Just plug in 1 and you'll get your point. So my point is going to be 0, 2. When t is 1, x is 0, and y is 2. All right, and then my slope. And, you know, as you get better at this, I'm okay if, I'm trying to decide if I want you to write out dy dt and dx dt. I think I do. In case you have to take a second derivative, then it's really obvious what your original dx dt was. So dy dt is going to be, yep, and dx dt is going to be 1. Dy dx is negative t to the negative 2 over 1. So when t is 1, the slope will be negative 1. And the equation of a tangent line is still a line in normal xy form. So y minus 2 equals negative 1 times x minus 0, or just x. All right, where do you think a parametric curve will have a horizontal tangent line? Okay, I'm hearing when dy dx equals 0, and I'm also hearing when dy dt equals 0. And you're both right, but it needs to be more specifically when dy dt equals 0, because dy dx is dy dt over dx dt. All right, so wherever dy dt equals 0. Yes, and dx dt will be the vertical. However, dx dt cannot equal 0. Because if both dy dt and dx dt equals 0, you've got this indeterminate form. Okay, so a horizontal tangent will occur wherever dy dt equals 0, as long as dx dt does not equal 0 at that same point. And therefore, we will have a vertical tangent whenever dx dt equals 0, but dy dt does not equal 0. Okay, and then the last thing is arc length in parametric form. Back in Chapter 7, when we were doing the area and the volume, we found had an arc length formula. Well, that was good for x's and y's, but if you have a parametric curve, then you have to use a different formula. And it looks really scary, and it's derived from the arc length formula in normal rectangular mode. And that arc length formula, just to remind you, was I don't know what we called it. I don't know if we called it A. Arc length was the integral from A to B, the square root of 1 plus f prime of x, the quantity squared. This formula is very similar. It's the integral from A to B, the square root of f prime of t squared plus g prime of t squared, where x is your f and y is, so basically it's x prime squared plus y prime squared. Square root of that. So really, in order to find this, We only need to have to be able to take the derivative of x and the derivative of y. So dx dt is going to be, that's kind of scary, 1/12 times, we could rewrite this as, we can rewrite x as 1/12 times 8t plus 8 to the 3 halves. So if you bring the 3 down, 1/8. So 1/8 times 8t plus 8 to the, what power? 1/2 times 8. Perfect. You're right. So this isn't as horrible as it looks. All right, dy dt, thank goodness, is a little bit easier. 2t plus 1. So the length from the beginning of this curve when t is 0 to the end of the curve when t is 2 is going to be the integral from 0 to 2. Square root of dx dt squared, and when you square that square root, you just get 8t plus 8, like Meredith was saying, plus dy dt squared. And I will let you type that into your calculator. Actually, I would let you type it in. It turns out that, okay, just go with me here. If you FOIL all of this, if you FOIL this out and combine all of your like terms, what you get is 4t squared plus 12t plus 9. Which factors into the perfect square 2t plus 3. The quantity squared. And the square root of 2t plus 3 squared is 2t plus 3, so we're really only integrating 2t plus 3 from 0 to 2. No, you got to integrate first before you plug in the 2 and plug in the 0. So it would be t squared plus 3t from 0 to 2. 4 plus 6 minus 0, so 10. Yay! But that one was easy, but those would be things that, unless it's a very, very simple equation, those would be things that I would let you use your calculator to integrate.